This is part 2 of a series on regularization of neural networks. In this video, we will look at how to apply activity regularization to a neural network model. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. In the last video, we looked at how to apply weight and bias regularization to a neural network. In this video, we will look at activity regularization, which applies regularization to the outputs of hidden layers. The activity regularization prevents overfitting by imposing a penalty on the outputs of each layer to prevent them from becoming too large. Let the outputs of the hidden layers be Q1 and Q2. Q1 and Q2 are respectively calculated as follows. Q1 is a function of W1 and B1, and Q2 is a function of W1, B1, W2, and B2. In this way, we add penalty terms for Q1 and Q2 to the existing loss function. In this example, we applied L2 regularization to Q1 and L1 regularization to Q2. This is the regularized loss function. Since W3 is independent of Q1 and Q2, W3 is updated using only the gradient of the existing loss like this. Since W2 is independent of Q1, the partial derivative of Q2 with respect to W2 is added here as follows. So W2 is updated as follows. W1 is used in both Q1 and Q2, so the partial derivatives of both Q1 and Q2 with respect to W1 are added. Updating W in this way prevents overfitting by not increasing the outputs of hidden layers. Bias B1 and B2 can be updated in the same way. This is more effective when there are many hidden neurons. This is because even if the weights are small, the output can increase if a lot of the dot product of Q and W are accumulated in a neuron. L1 activity regularization makes the output of some neurons 0, while L2 makes the output of neurons smaller overall. L1 activity regularization is most often used in sparse autoencoders to encourage sparse latent features that are the outputs of the encoder. This is to better capture salient features of the input data. Next, let's apply the activity regularization to our neural network using Keras regularizer. Let's create a binary classification model using the data used in the previous video. The data we will use is as follows. Create a neural network model. The input layer has 2 neurons, and the output layer has 1 neuron. And each hidden layer has 32 neurons. Create optimizer and regularizer objects. Learning rate is set to 0.001. And the regularization constant is set to 0.01. Create an input layer and then create the first hidden layer. Apply L1 activity regularization to this hidden layer. Then, the outputs of this hidden layer will not be large. And we create 4 additional hidden layers. The data is simple, but we intentionally added many hidden layers to the model to demonstrate the effect of regularization. We apply L1 activity regularization to these hidden layers as well. Finally, we create the output layer. We did not apply activity regularization to the output layer because the output values do not need to be small. We create and compile the model. Since this is a binary classification model, we used binary cross-entropy loss. And we used the atom optimizer. Fit this model to the training data. The number of iterations is set to 200. and the batch size is set to 20. Visually see the loss history. Finally, we measure the accuracy of the test data. The results are as follows. The results without applying regularization are as follows. You can see that the validation loss is increasing. That is, the data is too simple, but the model is too deep, resulting in overfitting. The results after applying regularization are as follows. The validation loss still increases slightly. The possibility of overfitting still exists. If your goal is to prevent overfitting, I think weight and bias regularization would be more effective than active regularization. Let's run this code. First, let's set the regularization constant to 0. You can see that overfitting occurs like this. This time, let's set the regularization constant to 0.01. The results are as follows. In the previous example, we applied activity regularization to the outputs of the activation function of the hidden layer. This time, let's apply activity regularization to the outputs before applying the activation function and check the results. Import the Keras activation class for the activation function. Apply the activity regularizer to dense without using the activation argument. This applies the regularization to the outputs before the activation function is applied. Then apply the activation function in this way. Let's check the results. We got similar results to the previous code. There was no performance improvement. Regularization is usually applied after the activation function. If for some reason you want to apply regularization before the activation function, you can do it like this. Next, let's apply W&B regularization and activity regularization together. Just specify kernel regularizer, bias regularizer, and activity regularizer together in the dense layer. You can see that no overfitting occurs like this. Let's run this code. The results are as follows. Next, let's look at how to impose constraints on the outputs of hidden layer. This can be implemented through activity regularization. For example, in the neural network below, we want to limit the average of Q2 to around 0.05. If a neuron's output is 1, we can say it is active. And if its output is 0, we can say it is inactive. That is, the output Q is a Bernoulli random variable. Let the output of the jth neuron of the second hidden layer be Q2J. M is the batch size of data. When M pieces of data X are input to the neural network, M pieces of Q2J are output. Let the average of Q2J be rho hat J. This notation means the value of Q2J when the data point Xi is entered. For example, we want to train this neural network so that rho hat J is around 0.05. Let's call the desired output 0.05 rho. Rho is a sparsity parameter, typically a small value close to 0. That is, we want the average output of each neuron in this hidden layer to be approximately 0.05. For the average to be as small as 0.05, the outputs of this hidden layer must mostly be near 0. This means that the outputs of this hidden layer become sparse. This is primarily used in sparse autoencoders. We'll look at sparse autoencoders later in the autoencoder series. To achieve this, we add a penalty term to the loss function. This penalizes rho hat j that deviates significantly from rho. The following KL divergence can be used as a penalty term. This KL is the Kullback-Leibler divergence between a Bernoulli random variable with mean rho and a Bernoulli random variable with mean rho hat j. Minimizing this makes the distribution of rho and the distribution of rho hat j similar. That is, rho hat j gets closer to rho. So the regularized loss function is as follows. The source of this content is this document. For more information on this, please refer to this document. Now, let's implement KL divergence regularization using activity regularization. This is commonly used in sparse autoencoders, but here we will apply it to our previous binary classification code. Write a custom regularizer for KL divergence regularization as follows. The inputs to this class are the regularization constant and the desired output, rho. Calculate rho hat j as the average of Q. Here Q is the outputs of the hidden layer. And then calculate the KL divergence. Rho hat values are truncated to fit this range to avoid zero denominators. Then return this regularization term. This will then be added to the existing loss function by Keras. Now we create the same neural network model as the previous code. L2 regularization is applied to the lower hidden layers. We then apply the KL loss regularizer we just created to the last hidden layer. The regularization constant is set to 0.1, and the desired output rho is set to 0.05. This will result in the average output of the last hidden layer being around 0.05. Create and compile the model for training. Then we create another model to check the outputs of the last hidden layer. Since this is not for training purposes, we don't need to compile it. Let's train this model and check the results. Once training is complete, input test data into this model and check the outputs of the final hidden layer. H-act is the output of the last hidden layer. Observe the histogram of H-act. The observations are as follows. The histogram, when rho, the desired output, is set to 0.05 is like this. As expected, the outputs of the last hidden layer are mostly close to 0. The average of H-act is 0.188. This is the rho hat. This is the result when rho is set to 0.5. The outputs of the last hidden layer is often close to 0, but the number of outputs exceeding 0 increases significantly. And the average of H-act is 0.392, which is larger than above. The average of H-act is close to 0.5. Applying KL divergence regularization in this way allows us to adjust the average outputs of the hidden layer. Let's run this code. First, let's set rho to 0.05. The results are as follows. This time let's set rho to 0.5. The results are as follows. Compared to previous results, the number of outputs greater than 0 has been increased. So far, we have looked at the regularization of neural networks through 2 videos.